With the account dimension, there are several properties to set that control the behavior of the accounts. We can set them manually, but it's a bit easier to use the Account Intelligence wizard. The first step of this wizard is to map the standard attribute types that Analysis Services understands to the actual attributes that are in the dimension. For example, the accounts attribute in our account dimension is the parent-child hierarchy that contains all of the accounts and defines the hierarchical relationship between accounts and account groupings, like different types of receivables that roll up to current assets that roll up as balance sheet accounts. Then we have the account name attribute type that we map to the key attribute, account in this case, which contains the actual name of the account. If we have an account number attribute, we can map that also. But we don't have to use an attribute type just because it's in the list, although at minimum we really need chart of accounts and account type. Speaking of account type, we'll map that as well. It's used to categorize an account as an asset, liability, and so on. The account type is important for aggregation over time, as we'll see shortly. Then on the next page of the wizard, we see a list of all the standard account types that Analysis Services understands. And then we map these to the distinct values that correspond to the account type column that we specified on the first page of the wizard. Now there is a way to modify the list of standard account types that I'll show you in the next demonstration. The account types that we set in the Account Intelligence wizard are used by Analysis Services to manage account type aggregation. When we use a cube browser to display account types by time, we can see the effect of account type aggregation. For example, assets and liabilities aggregate over time by using a last non-empty aggregation. This is one type of semi-additive aggregation. That means Analysis Services has special behavior when aggregating a date hierarchy, but aggregates normally by summing members of all other dimensions, in this case accounts. That means the total for a given quarter doesn't add up the 3 months belonging to that quarter, but instead uses the last month of that quarter that has a value, which in this case is March. If March did not have a value, but February did, then the quarter total would repeat the value for February. Similarly, the value at the year level for an asset or liability account uses the last non-empty quarter, which would be quarter 4 if it has a value, or quarter 3, and so on backwards through the year by quarter. Now, if none of the quarters for a year has a value, then the year also has no value. This is correct behavior for these types of accounts because they represent a balance at a point in time and do not accumulate over time. Statistical accounts are also typically based on a point in time, so these will also be set to use a last non-empty aggregation. On the other hand, revenue and expenditure account types use normal aggregation with the sum function. We add up these values over time, and so a parent member like quarter shows the accumulated value of its children, the months. Now it's important to remember that account type aggregation only affects how values get rolled up over time, from day to month to quarter to year. To get the behavior you see here, where we have last non-empty for some account types and sum for others, we need to configure the amount measure to use the by account aggregate function. However, it's important to note that this is available only in Enterprise Edition. If you have Standard Edition, you can achieve the same goal by building a lot of expressions into the MDX script of the cube, but you should have a good understanding of how to work with MDX and how MDX scripts affect the value that display when you browse a cube. Later, we'll learn about aggregation for the accounts themselves. The values that you see for balance sheet total and net income total and statistical accounts total are all incorrectly shown here because we still need to adjust some more properties. But first, let's go to a demonstration to apply what we've learned thus far.